All right, so let's pick up where we started or left off yesterday. So again, we said that work allows us now to classify new forces. So again, we have the conservative force, and again, the conservative force means that the work is path independent. So again, what does that mean? So that means, again, if I started off at a point and then I go to a different point, it doesn't matter the path at which I choose to go to those different points. So again, for example, let's say I start off here at A. So this is my vector A. And then I'm going to finish off somewhere down here at B. And let's say I go along two different paths. So in the first case, I'm going to go directly from A to B. So let's say along this path here. Okay, so this is going to be the work from A to B. And then let's say I go another path, let's say the green path here. So I'm going to go from A to some point C up here. So I'm going to go in this direction. And then in this case, I'm going to go from C to B. So in this case, we're going to have the work from A to C plus then the work done from C to B. These two things in conservative forces will be exactly the same thing. So again, it's completely path independent, which means it doesn't matter how I go from point A to point B. All that matters is I go from point A to point B. So, and then we have non-conservative forces. So non-conservative forces is work which is path dependent. So again, what that means is that these two works here would not be the same. So in this case, actually my work going from A to C and then going from C to B would actually be larger than my work going from A to B directly. And as I mentioned, in this case, what this means is that I'm losing energy or I'm adding energy, actually, either one would be fine, to the system. So I have two different works going from two different paths. So for example, let's say I'm losing energy from something like friction. So the longer I go, the more energy that I'm going to lose due to that friction. Now, in this case, I mentioned this also in class yesterday. What this means is, for example, if I was sliding a eraser across the table, so in this case, instead of going directly from A to B along the gray path, if I go from A to B along the green path here, what's happening then is you're losing that energy due to friction. So in this case, the friction is actually heating up the material that is getting hotter. And then as it gets hotter, it has to release that energy out to the universe in the form of what we call thermal energy. So this type of energy is what we call internal energy. So when an object heats up, or increases temperature, I should say, object increases temperature, it increases its internal energy. And eventually that increased internal energy will then cool back down by releasing its energy off as heat, but we'll talk more about that stuff later. So anyways, so again, conservative forces are interesting in the fact that since they're path independent and it doesn't matter how I go from point A to point B, it just matters that I got from point A to point B. What this means then is we can actually then define a potential energy from them. So conservative forces will allow us then to determine potential energies. Good. So how does this actually work? So the easiest way to talk about this is let's first look at gravitational potential energy. So for example, let's say I take my water bottle here. Actually, this is my daughter's water bottle. Grab the wrong one. But anyways, I throw this into the air. Okay. Not too much noise, so I don't wake anybody up. So in this case, when I throw it into the air, what happens is what? As it's moving upward, so this water bottle is moving upward, what we know is that what? Its kinetic energy is decreasing. And the reason for that is what? Because we got the gravitational force pulling downward. In this case, it's applying a acceleration in the opposite direction in which it's moving. And in this case, it's slowing down, right? So as it slows down, it's losing kinetic energy. But as we mentioned yesterday, energy cannot be lost. It has to basically go someplace else. In this case, where's that energy going? Well, the energy is going into a new form of energy, which is what we call the gravitational potential energy. So let's draw that. So in this case, again, let's say I start off with my ball or water bottle, whatever it is, at some initial heights. So let's call this, I don't know, y initial. I'm going to throw it upward. So it has an initial velocity of, say, v0. And then as this thing moves upward, let's do it this way. So as I move up, and now I get to this location here, where this has some new height to it. So let me just call this y final for now. It's now going to be moving with a new velocity. Let's call that velocity v. But in this case, again, v is less than the initial. So what this means then is that as it's moving upward, I'm losing my kinetic energy into potential energy, and a potential energy has to have something to do with its height, right? Because initially it's starting off with a lower height and it's finishing with a higher height. But as it moved from a lower height to a higher height, it has now gained potential energy while it has lost kinetic energy. So how does this actually work? So we can start off with our work kinetic energy theorem. So remember that work kinetic energy theorem says that the network is equal to the change in kinetic energy. We can use this to try to figure out what gravitational potential energy actually is. So let's think about this. So the only force which is acting on my object here, my ball or my water bottle or whatever it happens to be, the whole time is simply the weight, right? So as I'm throwing this thing upward, the gravitational force or the weight is pulling this thing down. So in this case, the only work I have on this is going to be my gravitational work, and that has to be equal to my change in kinetic energy. Good. Now let's think about the work. So again, remember that work by definition is equal to the magnitude of the force times the magnitude of the displacement times then cosine of the angle between the two. Good. So in this case, let's think about first of all our displacement. So here, since I'm starting off at a low height and I'm finishing at a high height, what that means then is that my displacement must then be pointing upward, right? So in this case, this is going to be my displacement. So my displacement vector is going to point from y initial to y final. So this is then when we're just going to call it delta y, since I already called it y. My gravitational force is the only force on this thing, so it's acting downward. And remember the cosine of the angle, where the angle specifically is the angle between the displacement vector and the force vector, which means in this case, it's going to be equal to 180 degrees. Right? Because my displacement vector is upward, my gravitational force is downward, so they're anti-parallel to each other. So that's going to be 180 degrees. So in this case, I'm going to have then that this is going to be my gravitational force, right, times then my displacement delta y, times then cosine of 180 degrees is then equal to my change in kinetic energy. Now, from here, we know cosine of 180 degrees is equal to -1. So this is going to be equal to negative mg, since that's gravitational force, times my displacement is then equal to my change in kinetic energy. Good. Now, from here, again, our claim is that as this thing is moving upward, what's happening then is it's slowing down. And as it's slowing down, it is now converting its kinetic energy, since kinetic energy is getting smaller, right? Starting off with a large number and finishing with a small number, most of the time 0 in this case, when it stops momentarily at its highest point. So it's decreasing its kinetic energy. So this thing is actually getting smaller, while this portion here is then getting bigger. So the negative sign just means that in this case, the kinetic energy is getting smaller. So I need this negative sign to overcount for the fact that the kinetic energy here is getting smaller. So again, the right-hand side is something which is a negative number, since the change in kinetic energy is negative. mg delta y is going to be positive since it's moving upward. So that negative sign here has to account for the fact that the kinetic energy is getting smaller. So again, ultimately, all it means is that as the kinetic energy is decreasing, my what we call potential energy is then increasing. So from here, we can then identify that this portion here is actually the potential energy. So what I'm going to say then is that here I have my change in potential energy is then simply equal to my mg delta y. So this is what we call our change in gravitational potential energy. Or if I wrote this out, this is going to be then mg times the final height minus then my initial height, which is then equal to, on the left-hand side, my final gravitational potential energy minus my initial gravitational potential energy. Now, if I identify the two sides together, what this tells me then is that my gravitational potential energy then must be simply equal to mgy. So this is what we call our gravitational potential energy. So what this tells me then is how much energy that an object has relative to some initial points, right? Yeah. Oh, I'll come back and talk about that in just a second. Now, the other thing we can get out of this is since the left-hand side here is simply equal to the work, so this is the work done by the gravitational force, this also tells us a relationship actually between the work and the change of potential energy. So again, what this says is that our gravitational potential energy is equal to our kinetic energy, but the negative of our change in gravitational potential energy is then equal to the change in kinetic energy. So using these two things, what this also tells me then is that what? Work is equal to negative the change in potential energy, at least in the gravitational sense. Now, this statement is actually always true for any type of work. So one big thing we can get out of this is that work is equal to negative the change of potential energy. So this is actually going to give us a unique definition for what potential energy is. So what this ultimately tells me then is anytime I have a conservative force, we can use the work to then define our change of potential energy, or at least what our potential energy is. So again, this says that our work is equal to a change in potential energy with a negative sign, or I can rewrite this then as our change of potential is then equal to negative of the work. Now, for a general force, as we know, the work is equal to what? The integral from A to B of the force dotted by the path, right? The path as we go from one point to another point. So in this case, using our general sense of work, we can define our then change of potential energy as negative the integral, again, from A to B of our force dotted then by our differential length along some given path from point A to point B. So again, if I draw this out, so this is my X direction, say my Y direction and my Z direction. And in this case, my point A is going to be some vector. Point B is going to be some other vector. And then again, I'm going to go from A to B along some pre-described path. And then DL here is going to be a differential length along this particular pre-described path. So again, as long as I have a conservative force, which is what this guy is, as long as I know what the value of the force is, I can then easily find my change of potential energy, or in particular, just the potential energy for any given conservative force. So again, as long as I know what the conservative force is, I can then find the potential energy associated with that particular force. And we'll do that for a couple of examples here in a second. But let's go back to our gravitational potential energy here for a second. So again, what this says is our gravitational potential energy then has to do with the height above some sort of reference point. Now, notice here, there's a huge ambiguity here. What's that ambiguity? So the ambiguity is, well, what height am I actually talking about? So meaning that this height y here is only the height above some point at which I call 0. But I can call any point 0 which I want. So for example, I can say that initially here, I could say that this water bottle that I'm holding has some potential energy relative to the height of the table at which I'm sitting at. Or I could say it has some potential energy relative to the height of the floor, right? So what's the difference? Well, the difference is relative to the table, it has a much higher or smaller distance, I should say, from the table to where the bottle is versus the floor to where the bottle is. So if I'm talking about from the top of the table, I'm going to have a small potential energy versus from the floor, I'm going to have a higher potential energy. Now I'm actually on the second floor of my house, which means if I relative to the first floor of my house, it has an even bigger potential energy. Or I could do from sea level, it has a bigger potential energy, or from the center of the Earth, then it has a huge potential energy. So the point is that this ambiguity comes from the fact that we have no actual reference points. We have to choose a reference point at which it is that we're talking about. Now, ultimately, what that means then is that the potential energy of an object actually mostly has no meaning to it. Because as I choose different reference points, that chooses a different potential energy, which means that I'm going to have a different potential energy given every different reference point. So for somebody just to say that an object has 10 joules of potential energy, it doesn't really tell you that much. But as we can see here, when it comes to the work, and in this statement of throwing this bottle or eraser or whatever it is that we're throwing into the air, what's actually more important is actually not the absolute value of the potential at given points, but it's actually the change in potential energy. So the way we're going to get around this ambiguity is to not care about the actual value of the potential, but only to care about changes in potential. So what matters to us is not the actual value of the potential energy at any given point, but how it changes going from one point to another point. This is what's actually going to be important to us. Because again, of this inherent ambiguity in the definition of the energy itself. Okay? So in the energy, regardless of whatever the potential energy happens to be, it turns out that there's always going to be this ambiguity inside of it. Now, this is actually also true in kinetic energy. We just didn't talk about it before. And the reason for that is, I'll kind of skip to this. So again, I'll put a note on here that there's ambiguity in kinetic energy as well. The reason for that is what? We defined kinetic energy, again, as the energy that an object in motion had. So we said that the kinetic energy was equal to 1/2 the mass times the velocity squared, which means that if this thing has a mass m and it's moving with some velocity v, then this thing has a kinetic energy. But the question now becomes, well, whose velocity am I actually talking about? So obviously I'm talking about the velocity of the object, but who's watching this thing as it's actually moving? So for example, if I'm sitting here stationary, watching, say, somebody throw a ball, then I would assign the kinetic energy based off of the reference of the velocity that I see. However, if I was driving in a car, the same time somebody was throwing the ball, I'm going to see a different velocity due to the fact that I'm moving as well. So what I'm going to see is what we call the relative velocity, the difference between the velocity of the ball and my car. Or if we take into account that the Earth is actually rotating, well, in that case, then I would take the rotation of the Earth's speed plus the speed at which I'm throwing the ball, which then massively increases the amount of velocity this thing has, which massively increases its kinetic energy. So here, the ambiguity lies actually within the velocity and how we're actually defining the velocity relative to what something is doing, right? So who is looking at the velocity? So who is defining this velocity? Because depending on who's defining this velocity is going to change the value of velocity, which is then going to massively change actually the kinetic energy as well. So again, if I'm driving in a car going as fast as the ball is moving, then as far as I'm concerned, the ball is stationary. So it has 0 kinetic energy, it's not moving. But if I'm stationary and the ball is being thrown at, I don't know, let's say 5 meters per second, it's going to have a, okay, kinetic energy. It's not too big. And then if I take into account that I'm outside of the Earth, watching the Earth rotate, which has a huge velocity, at least tangential velocity on the outside, and then I'm throwing a ball on top of that, right? So it has an even bigger tangential velocity. So the kinetic energy is going to be enormous. So the point is that kinetic energy has an ambiguity just like this new thing, potential energy. But at the end of the day, what we care about is not the actual values of these things. What we care about is how they change going from point A to point B. So this is going to be important to us. The changes in these energies, which gets rid of the ambiguity at which it is that we have to define these particular quantities. Good. So good. So let's go back to potential energy then. Good. So for potential energy, we now have that the work then is equal to minus the change of potential energy, or more particularly, the change of potential energy is equal to the negative of the work, which again is going to be equal to negative of the integral from A to B of the force dotted by the differential length. Good. So this is then, again, our definition of what potential energy is. So as long as we know what the conservative forces that we're actually looking at, we can now use that to now define what is our potential energy. And then from that potential energy, we can then do other things with it, which we'll talk about in a little bit. So let's look at this and let's do a couple examples. So our first example is going to be, let's determine, again, the gravitational potential energy. We already know the answer to this. We just wrote this down, but again, let's just see how this works just to get a little bit more comfortable with it. So we have, in this case, let's look at the change in gravitational potential energy. So this is then going to be equal to, according to our here, negative the integral from the initial position to the final position of the gravitational force, again, dotted by our differential length. Good. So in this case, again, let's say that here's my object. It's going to be moving upward, so that this is my initial height. This is then going to be my final height. And in this case, we know our force is acting downward. So this is mg. So this is our gravitational force. So first of all, if I look at my differential length, I'm going to cut this way. So this is my dl. It's going to be pointing upward along the direction at which the path of the particle is moving. So in this case, I can rewrite dl as simply equal to dy in the y hat direction. My force here, if I wrote it in unit vector notation, this is then going to be negative mg in the y hat direction, right? For the j hat direction, since it's pointing downward. Now, if I dot these two guys together, what that does is it's going to give me this negative sign. So this is then going to become equal to, so my negative sign is going to cancel this negative sign. So this will be equal to the integral from the initial position to the final position of mg dy. Right? So again, my dot product between these two, let's write it out. So fg dotted by dl, it's going to be the same thing then as what? So I'm going to have mg with a negative sign times, and then dy all times j dot j. But again, j dot j we know is just equal to 1. So that's where that negative sign comes from. So again, the negative signs are just going to cancel each other. mg is simply a constant, so I'm going to get mg integral from the initial position to the final position. Then dy, integral of dy is simply dy, evaluated from the initial position to the final position. So I get mg times y minus y initial. And again, my left-hand side is the final gravitational potential minus my initial gravitational potential, which again tells me that the gravitational potential is then mgy. So same result that we had before. Let's do another example. Next one is what we call spring. So again, we already saw spring forces, but let's look at spring potential energy. So it turns out springs actually are conservative forces. Reason for that is that when I compress it and it goes back to its equilibrium position, I'm not losing any energy. All that's happening is when I compress the spring, I'm gaining potential energy. So I'm causing it to be able to do work. And then in this case, when it goes back out and gets to 0, I have lost all the potential energy, and then it has all gone to kinetic energy. Or same thing, if I elongate it, I'm increasing its potential energy for the ability to do work. So remember, our definition of energy is the ability to do work. So in this case, again, I can use a spring by compressing it and then letting it go and act like a hammer, for example, to do work onto a system. So let's look at the spring potential energy. So I want my change in spring potential energy, that is equal to negative of the work done by the spring. So it's then going to be equal to what? Negative of the integral from the initial position to the final position. Then our spring force dotted then by our differential length. Go. So let's talk about this one. Good. So in this case, again, remember that our spring force is equal to a negative k times x. In this case, we're going to write dl then is equal to what? Dx in the I hat direction. So if I wrote out this one actually differently, this would be kx in the I hat direction. Again, in this case, what I'm assuming is that what? As I take my spring, so let's say this is initially my spring, so this is at its equilibrium position. And then as I compress it to now a new position, so let's call this x0. Again, what we know is that the force is trying to push it back to the original equilibrium position, which means it's acting in the opposite direction at which it is that the displacement is, right? So in this case, my displacement is actually in this direction, right? So this is going to be my dx. So these two are going to be in the opposite directions. So good. Again, my dot product is simply going to give me a negative sign. So that negative sign is going to cancel this one. So this is going to be the integral from the initial position to the final position of then the spring force, which I'm going to get a k times x times then my dx. All right. K is a constant, so I can pull that out. So I'm going to get a k integral from the initial position to the final position of then x dx. Integral of x dx is x squared over 2. So this is then going to give me k over 2 times then x final squared minus x initial squared. Again, this is then going to be equal to 1/2 k times x squared minus 1/2 k x initial squared, and that's equal to the final spring potential minus my initial spring potential. Again, identifying these two terms, what this tells me then is that my spring potential is equal to 1/2 k times x squared. So this is what we call the spring potential energy. Now, since this thing has an x squared to it, notice what this means is it doesn't matter if it is compressed or elongated, I'm increasing its potential energy. So whether I compress it or I elongate it, it doesn't matter. I'm doing the same thing. I'm increasing its potential energy, which is why it comes with a squared, because it doesn't matter on actually the direction. Now, the other way we could have got this is we also knew that the work done by the spring was equal to 1/2 k x initial squared minus x final squared. So we could have actually just negated this to get this, but again, it's more fun to actually do the integral. So let's look at that. So good. So these are our different types of potentials that we can look at, or different types of potentials that we can use based off of these conservative forces. Now, why do we care about all this stuff? Well, we care about all this stuff because now, if we think about this, we actually have two different types of energies based off of two different types of works, right? So we know that from the work kinetic energy theorem, we have work, and I'm going to call this kinetic work, is then equal to the change in kinetic energy. So I'm going to call this kinetic work. This is the work associated with an object, which is motion. Now we have a potential work. So I'm going to call that potential energy work or potential work. And we know that's equal to minus the change of potential energy. So let's call this potential work. Now, let's first switch signs. So I'm going to bring this to that side. And now let's add these two things together. So what this says then is that my change in kinetic energy plus my change in potential energy, which is what we call the change in total mechanical energy, is then equal to the kinetic work minus then the potential work. Okay, so the work done by the change in kinetic energy and then the work done by the change in potential energy. Now, if I have a system which has nothing acting on it, so I have only conservative forces. So for only conservative forces, what happens in this case then is that the work done by the kinetic is equal to the work done by the potential, which means in this case, my right-hand side would then be equal to 0. Right? So in this case, I would have my change in mechanical energy, which would then be equal to my change in kinetic energy plus my change in potential energy would then be equal to 0. However, if we have non-conservative forces, for example, friction, associated with this as well, what happens in this case then is that what my work done by my kinetic will not be the same as the work done by the potential. So what does that mean? So what that means is, for example, if I took a water bottle and I dropped it, but then I caught it, and then I slowly let it go down to the ground, What's happening in that case is my change of potential energy stays the same because I had my same height change. But since I'm artificially taking energy out of the system, what that means then is that I'm losing energy due to this artificial taking away energy from the system, causing it to move to the ground slower than what it should actually be moving. In this case, then, what happens then is that what? The work kinetic minus then my work potential will no longer be equal to 0, but it's going to be work equal to something else, which is what we call the work done by the non-conservative force. This is then work done by non-conservative force. Whatever is taking that energy away from the system. In this case, then, we're going to get that our change in mechanical energy is then equal to our change in kinetic energy plus our change in potential energy. And that's going to be equal then to the work done by the non-conservative force. This thing here is the most beautiful, sexy, most attractive equation you'll ever see in your whole entire existence. This thing is what's known as the conservation of energy. When you see this, you should weep, you should hear angelic sounds, because this thing is the most powerful thing that we have learned in this class so far. So as we made a big point out of when we talked about the work kinetic energy theorem, is that work kinetic energy theorem did exactly the same things we had already done in this class, i.e. forces and kinematics, but without the requirements of the fact that we had constant acceleration. This thing here does exactly the same thing. So this is basically the same thing as the work kinetic energy theorem. However, it's actually easier. And the fact that I'm not going to make direct reference to the work at all, the only thing I'm making direct reference to when it comes to work is if I have a non-conservative force. In that case, I do have to know exactly what the work is by the non-conservative force. However, this thing is actually more powerful than the work kinetic energy theorem in the fact that, again, I don't care about the work. The only thing I care about is the kinetic energy at the beginning of whatever the object was that was moving, and what it does, its kinetic energy at the end, and its potential energy at the beginning and its potential energy at the end. I don't care about the work. I don't care about how it went from point A to point B, which means I don't care about the direction of the displacement. I don't care about how it's moving. Is it moving upward? Is it moving downward? Does it move up first and then down? I don't care about any of the specifics that happens in between. All I care about is what is it doing at the beginning and what is it doing at the end, and that is it. This also, just like work kinetic energy theorem, contains all the information about the forces, it contains all the information about the kinetics, but it doesn't care about how it moves going from point A to point B. All it cares about is what is it doing at point A and what is it doing at point B. And just like the work kinetic energy theorem, it's a scalar quantity, which means I don't care about directions, I don't care about forces, I don't care about any of that stuff. All I care about is what's it doing at the beginning and what is it doing at the final. And I don't care about any of the in-between specifics. So this thing is even more powerful because one, it's easier to use, and two, it doesn't require as much thinking. All I need to know is what's it doing at the beginning and what's it doing at the end, and that's it. So this thing is the most powerful thing that we're going to be using for the entire semester. So, whoops, big one. I am beautiful. So this is our conservation of energy. So now let's make a few notes of this. So first of all, the work done by the non-conservative force, this thing can be one of three things. It can either be 0, and this is when I have conservative forces. So meaning there's no energy which is being taken or added to the system. So in that case, it just means that the change in kinetic energy is equal to negative the change of potential energy. It can be less than 0. This is what we call dissipative or dissipative. So anytime I have dissipative forces, this thing's going to be less than 0. So dissipative forces will be things like friction forces. So friction, air resistance, etc. Anything that's artificially taking energy out of the system. This could also be something like tension. So for example, if I had a block sliding down a inclined plane and then I grabbed the tension and pulled back on in the opposite direction, it would be taking energy away from the system. So anything that takes energy out of the system artificially is what we call a dissipative force, which is going to lead to a negative non-conservative force, means it's taking energy away from the system. Or the work done by the non-conservative force can actually be additive. What does that mean? So that means that I could be adding energy to the system. So what does that mean? So that means if I took this water bottle and I dropped it and it's falling towards the ground and then I slap it downward out of the air, I'm going to cause it to move faster. So that means my slapping in this case is going to add energy to the system, which means that it's going to gain energy. So by the time it reaches the ground, it's going to be artificially moving faster than it should have been if I only dropped it a certain distance. So this is our work done by a non-conservative force. So a non-conservative force can be one of these three things. So again, it can either be zero, meaning we have only conservative forces, so no energy is being lost from the system. It's only going from kinetic energy to potential energy or potential energy to kinetic, depending on how the object is moving. It could be negative, means it could be dissipative forces. So I can have something taking energy out of my system. So again, friction, air resistance, tensions, things like that. Or it can actually be additive, where I'm adding energy to the system. I'm causing it to move faster than what it should be after it has fallen a particular height. So this is what we call conservation of energy. So conservation of energy takes all of these things into account and allows us now to be able to solve for these, whatever it is that we want. But again, it doesn't have the requirement of the fact that I have to have a constant acceleration. It's completely independent of the acceleration. Nothing in there refers directly to the acceleration. So it doesn't matter if it is constant or not constant, as we have seen, because again, going back to our spring potential, the spring potential, we know that this thing has a non-constant acceleration. So in this case, I don't have to have a constant acceleration because all I need to know is what's the potential energy. In this case, it would be the spring potential energy, and that's it. Okay. So basically, all we're going to do from here, I don't know how much time I have left. I haven't been looking at my clock, so I don't know. So let's at least do a couple examples, and then I'll call it a day, and then we'll pick up some more examples. But the idea now is just to get used to doing these problems, okay? So before we start doing these problems, let's talk about some steps. So how we're going to approach all of these different problems. So step number one, again, is we're going to, as we always do, draw. Now here, we're going to draw very particularly. So what I want to do is I want to draw what's happening initially. If I know how to spell initially. So I want my initial picture, what's actually happening, and then I want to draw my final picture. So basically, I want to know what's it doing at the initial point, what's it doing at the final point, or what's it doing at point A, and what's it doing at point B. Okay. Step number two. Identify potential energies. So what do I mean by that? So what I mean by that is, was there a change of heights? So is there a change of height? Answer is yes. Then there's a gravitational potential energy. Was there a spring involved? Yes. Then there's a change in spring potential energy. Those are the only two potentials we know so far. Those are the only two that we're going to need for a little while. So in this case, I just want to know what potential energies do I have? Kinetic, all I care about is how fast it's moving. So in this case, first I just need to know what types of different potential energies do I have. So again, the only two we know so far, we'll change this later, but we're at gravitational potential and then spring potential. So again, is there a change of height? And then is there spring? Good. Step number three. Non-conservative forces. Do I have any non-conservative forces within inside of this problem? So in this case, if I have no non-conservative forces, then the right-hand side is simply going to be zero. That's it. If the answer is yes, I have non-conservative forces, what is it? And what's its work? So I need this for my conservation of energy. Step number 4, apply conservation of energy. Step number 5, solve for whatever it is that I want. Okay. Good. So let's use this and let's do a couple examples. So the first example I'm looking at says that I have a driver of a car traveling at some initial velocity slams on his brakes to avoid a colliding with a stopped truck. Okay. So here is my car. Okay, so there's my car. Great, so there's my car. So mass of the car is equal to 1,000 kilograms. And let's say initially it's moving to the right. And this thing is moving with some additional velocity. Let's call that v car, which is equal to 35 meters per second. Okay. And some distance away is going to be a truck. I'm going to draw this as a pickup truck, I guess. There we go. There's my pickup truck. Cool. And this guy is stopped. Okay. Now, we're told in this case then is that this guy's going to apply his brakes and the greatest amount of friction force that he can get in the opposite direction, in which it is that he's moving, F sub k is equal to 8,000 newtons. Great. Cool. So first thing I want to know then is for part A, what is the minimum distance, delta x min, that it takes for the car to stop? Okay. So this is what I want to know. So what is the minimum distance to stop? Great. Now part B, and we want to know, so if the initial distance, so let's say the distance between the truck and the car is only equal to 30 meters, what then is going to be the final speed at which the car hits the truck? Okay. If it hits the truck, which, well, of course, already alluding to you that it does hit the truck. My truck is awful. There we go. Slightly better truck. Good. So good. So now in this problem, of course, this has a constant acceleration because the only force is going to be this friction force, which we're told is a constant force, which means it's going to have a constant acceleration, which means we could find the constant acceleration and we could use that into our third kinematic equation to then find what is the minimum distance. We could do that in this case, but we're not going to because we have a new toy. That new toy is our conservation of energy. So let's use our conservation of energy. So let's draw. So again, step number 1, we're going to draw. So in this case, I'm just going to draw a box. There's my car. So my car is moving again to the right. So with initial velocity of the car. Okay. And we're going to say it has the friction force. This is my friction force. So this is my F sub k. Okay. So this is my initial picture. My final picture then is going to be what? This guy. He is now stationary. So we know the final velocity is going to be equal to 0. This entire time he had the friction force acting on him, and he has gone a distance in this direction of then delta x minimum. So this is my initial picture and my final picture. So good. So first things first, that was step number 1. Step number 2, we're then going to identify any changes in potentials. In this case, I have no change in potential because this thing is starting and finishing on the same horizontal line, which means my change in gravitational potential is simply equal to 0. There's no spring, so that means also my change of spring potential is equal to 0. So I actually have no potential energies in this problem. Good, so that's step number 2. Step number 3, is there work? Well, by a non-conservative force. So is there a non-conservative force in this case? The answer is yes, because there's a friction force. So in this case, my work done by my non-conservative force is then going to be equal to the work done by the friction force. Okay. So my work done by my friction force then is going to be equal to what? Negative. I'll do it in steps here. So this is going to be my friction force magnitude times my displacement, which is delta x min, times cosine of the angle between the two. But in this case, since the friction is to the left and delta x min is to the right, so that means they're 180 degrees rotated from each other. So this is then going to be equal to negative my friction force times my delta x min. Good. Step number 4, we're now going to apply conservation of energy. So this is my change in kinetic energy plus my change in potential energy, which we know is simply equal to 0, is then equal to the work done by the friction force. So my final potential or kinetic energy is going to be 0 minus my initial, which is 1/2 mv car squared, then must be equal to negative of my friction force times delta x min. These two negative signs will cancel out. From here, I can solve for delta x min. So I get that my minimum stopping distance then is going to be equal to the mass of the car times the initial velocity of the car squared divided by twice the friction force. Plug in my numbers. What I find in this case then is this works out to be 76.5 meters. Okay, so this is my minimum stopping distance. Good. So part B, we're told that the distance actually between the car and the truck is only 30 meters, which is less than the 76.5 meters. So it's going to hit, right? So what I want to know is, again, how fast is it going? So again, let's draw our pictures. So again, initially, here's my car. Here's my car going in this direction with the car. Again, it has the friction force acting on it in this direction. So this is F sub K. At the end, my car is going to be going over here. So basically the same picture as before, except the difference now is that the final velocity will no longer be equal to 0, but it's just going to be some velocity v. Okay. Good. So the only thing that's going to be different now is if I go back to my conservation of energy, is that my final velocity will no longer be 0. It's just going to be non-zero, which means my final kinetic energy is not going to be 0. But everything we did up to that point is still exactly the same. So let's do all the same stuff again. So we can have our change of kinetic energy plus our change of potential energy, where again, we have no potential energy, is again equal to the work done by the friction force. Only difference now is I have 1/2 mv squared, where that's the final velocity, minus 1/2 mv initial, or car squared, is then equal to, again, negative of the friction force times, in this case, not x min anymore, but just that distance d. So this is the distance d between the truck and the car. So the total distance at which the car traveled while the force of friction was actually acting on it. So good. So from here, I want the final velocity. So all I'm going to do is add the second term over to the right-hand side and then multiply by 2 and divide by the mass and take a square root. So this tells me that my final velocity is going to be the square root of 2 divided by the mass times 1/2 mv car squared minus my friction force times the distance. And this is my final velocity. Plug in my numbers. What I find in this case then is this works out to be 27.3 meters per second. So this is the final velocity that the car has by the time it hits the truck. Let's see. Actually, I think I'm going to stop here. So we'll do a whole bunch more examples then tomorrow in class. So on Friday. So yeah, so let me know if you have any questions, especially at the beginning of class tomorrow. We'll answer a bunch of questions anybody might have. Otherwise, if I can find some time, which I should, hopefully before all my kids wake up, to set up a Blackboard, ask some questions for you guys on Blackboard, do like a little mini quiz, make sure that kind of understand things that are happening. Then I'll also assign that due for tomorrow. So anyways, let me know if you have any questions. You can also put those, because this is going to be on YouTube, so you can put those in the comment section down below, or wait till you're in class. Either way is fine. And yeah, we'll go from there. So I will see everybody tomorrow.